Okay, I kind of lied to you. Not intentional, I'm sorry. I said the next video we'd be getting into R, and I totally forgot we need to talk about variance explained first. So let's get into it. So we've heard the term over and over again, variance explained. What does that mean? So variance explained is a proportion that ranges from 0 to 1. 0 means you have explained 0% of the variance, and 1 means you've explained 100% of the variance. 0 is the worst we can do, 1 is the best we can do. So let's say that you were just fascinated and want to predict people's height. If we knew nothing about the data, the best we could do is use the mean to predict somebody's height. And let's say the mean is 5'6", which ends up being 66 inches. And so we use that to predict people's height. And here's a graphic to illustrate that. But people are going to deviate from that. People are going to be taller, people are going to be shorter. But why? Why is that person shorter? Why is that person taller? With no other information about our data but the mean, we cannot explain the reason why that person is shorter and that person is taller. Or we cannot explain the variance from the mean. So we would say our explained variance is 0. So when you use just the mean to predict a score, your explained variance is 0. We cannot explain why they deviate from the mean.
But never fear, we have statistics
to guide us and help us out. Let's say we had a predictor, height. So here's an example. Notice in this example how much closer we are to predicting individual scores. So let's look at this person with our existing model, which is represented in red, which is just the mean. We were in error by this degree. On the other hand, when we add a new predictor, we are in error by this degree, which is a much smaller amount. In other words, we have explained some of the variance, or we have explained why that person deviated from the mean. Because they're taller. And the closer we get to predicting their score, the more variance we have explained. So again, with a mean model where you're just predicting based on the mean, the explained variance is 0. And if we have explained 100% of the variance, or another way of putting that, if our R squared is 1, we have fit every single individual's score perfectly. Now with mixed models, it's slightly more complicated. And the reason why it's more complicated is because we have multiple sources of variance. You remember before when we saw something that looked like this? We have variance around the fixed intercept, and we have variance around the individual scores, or the residuals. We could also have variance about the slopes too. Individual scores differ from their group's predicted mean. Like in this situation, we call this residual variance. Here, each of these data points on the left deviate from the green dot here, which represents the fixed effect, which represents that person's average alcohol consumption across all time points. So these deviations are exactly the same as the deviations we showed in the height versus weight example. So these sorts of deviations are exactly the same sort as these sorts of deviations. We call this residual variance. Also, each cluster's mean deviates from the fixed mean. Like in this example, the deviations of these lines from the black solid fixed effect line, we call intercept variance. And then we could also examine the deviation of the slopes. So like in this example, each cluster's slope is different from the fixed effect slope, and this is represented by slope variance. And just like before, we asked why. Why are some people taller? Why are some people shorter? We could do the same with the intercepts. Why does this cluster differ from the fixed effect? Why do these dots deviate from their group's mean? Why do these clusters' intercepts differ from the fixed mean? Why do their slopes differ from the fixed slope? And just like in regression, the more predictors you add, the better your predictions will be, and you will explain more of the variance. But the question becomes, how much better are we explaining the variance? And so the interpretation of the change in R squared is going to be the same for mixed models, we just have different sources of variance to explain. So we can actually do this in R. Let's take a look.
We're going to start by loading flexplot, as we always do, as well as the LME4 package, which allows us to do mixed modeling. And then, by the way, if you're trying to follow my examples before with the LMER, it might not have found it. I didn't even think about that until now. You got to install the LME4 package before doing that. And then we're going to type data math, and what that does is that just loads the math data set. And I'm going to fit a baseline model, which again, that means we have no predictors. And then I'm going to compare that to a model that has socioeconomic status both as a fixed and a random effect. And we know that because SES is here in the random effects section and here in the fixed effects section. And implicit in all this, there's also a fixed slope, or a fixed intercept and a random intercept. And then once we do that, we can run the model.comparison function. and you should get something like this. I believe this relies on flexplot version 8.6 point something. I believe. Let me check real quick. 8.0.8.6.1. I made a recent update that gave p-values in addition to everything else. So yeah, we see the standard stuff. We got the base factor, and the base factor is favoring the socioeconomic status one by quite a bit. And the p-values say the more complex of the two, which is the SES model, is favored, and we get the predicted difference. I'm not going to go into details on all this stuff right here, and instead I'm going to talk about the R-squared change, because that's what this video is about. So we have residual, and what we see is that we explain 6% of the variance in the residuals, and again, those are the deviations of each dot from their cluster mean. So we explain 6% of that variance with SES, and we explain almost 44% of the variance in intercepts by adding SES as a predictor. But we could also do a visual of that and kind of get a visual representation of the variance explained, and so we can use compare.fits, and I'm just going to put socioeconomic status on the x-axis and then school in panels. In panels? Yeah, it's going to panel it. It defaults to 3 random effects, or 3 clusters. You can specify more if you want to. And then I'm just going to be comparing the baseline to the socioeconomic status model. And if I were to do that, I would get this lovely plot. And so we've got the green or blue line, whatever you want to call it. Clearly, this is fitting the data much better than the red line. And again, the red line says that there are no predictors. We are just trying to detect differences in means. And of course, all the schools are going to have differences in means. So that's cool. There's our visual representation of the 6% of the variance explained in the residuals and the 44% explained in differences from the fixed mean. Let's go ahead and add another predictor. And let's say that that was our model from the beginning. We wanted to compare a model with just socioeconomic status to a model that has SES and minority status. And that's really our substantive question of interest. Basically saying, if we control for socioeconomic status, is there a difference in minorities and how well they do in math? And so we can run that model that includes minority status as a fixed effect. I'm not putting it as a random effect because, again, usually you don't put categorical variables as a random effect, although you could if you suspect that the differences between minority and non-minorities differs depending on what school you go to. And I could see that. Maybe you have some affirmative action policy or something like that to help out those who are struggling with math, particularly if they're minorities. And if we were to do a model comparison on that one, minimize that. We are now it's actually important to think about what the baseline model it is comparing against. So this is comparing minority with socioeconomic status to one that is just socioeconomic status. And so relative to a model with just socioeconomic status, adding minority improves or explains an additional, looks like 8% of the residual variance and 50% of the intercept variance. Now remember this one right here, the socioeconomic status versus baseline model, we already reduced the variance quite a bit. These two aren't going to be comparable just because they have different denominators. This one has a denominator with socioeconomic status as the variance explained, whereas this one has baseline as the denominator of variance explained. But that's pretty big, I'd say. So we are improving our fit by quite a bit, it seems, by adding minority. And we could also look at the Bayes factor. It too favors the minority model, as well as the p-value. And let's go ahead and get a visual of that one. Why not? And so now we get a lovely model. And remember how I said the denominator is different. So even though the change in R squared looks pretty striking, it's even bigger than the change in R squared was for the first model comparison. But this model comparison, again, has a totally different denominator. So in some places, the differences are fairly minor, like right here and right here. Some, they're a little bit bigger. But in either case, we do see differences in prediction. And again, the model comparison metrics tell us that we probably ought to favor the full model, or the model with the minorities, or the model with minority as a predictor.
All right, wasn't that fun? With that, let's review our learning objectives. Number 1, understand what variance explained means. Again, it means our improvement in prediction relative to just using the mean. Number 2, understand why mixed models are slightly more complicated. The reason why is because we have multiple sources of variance. We have residual variance, we have intercept variance, and we have slope variance. And number 3, know how to use the model.comparison function in flexplot to be able to estimate the variance explained for each of these different components. And with that, I'll see you next time.